when we think of muscarinic receptors, we have to realize that these muscarinic receptors use G protein coupled receptors to assist in this transmission. And so what's going to happen is I'm going to explain the alpha receptor first. So what I like to do when I explain this is I like to draw it out. And so I'm going to draw it out on the whiteboard, and I'm going to put this in full screen so I have more space to show you guys. So what's going to happen is we have our, let me draw in here. So we have our phospholipid bilayer here. And it's going to look really similar to our G protein coupled receptors that I've drawn out previously. But that's okay, because remember, the muscarinic receptor is a different form, if you will, of a G protein coupled receptor, or of a G protein coupled receptor. So remember here, we have our alpha subunit. So what happens with our alpha subunit and G protein coupled receptor? And if you remember, Children always says, remember, alpha, A, and beta, gamma, you have a lot of C's. So what she's referring to is the proteins that are found in the phospholipid bilayer. So with alpha, we're going to have, so I'm going to label G protein here. So this would be our receptor there. So what she's talking about when she's talking about alpha AAA, that this protein in the phospholipid bilayer is going to be called adenylate cyclase. I'm going to write that out for you guys to see. So we have adenylate cyclase here. Okay. And so now that I've labeled everything for you guys to see, I'm going to start to explain the process of the muscarinic alpha receptor. So what's going to happen is we're going to have our ligand binding to our G protein, and normally it's going to be acetylcholine, or ACH. And so we have our ACH binding here onto this G protein, and we're going to have our alpha, our beta, gamma subunits here. So knowing this is the alpha receptor, only the alpha subunit is going to leave and bind to adenylate cyclase. So our alpha subunit has binded to our adenylate cyclase, and I'm going to label that with an A just so I don't have any confusion. And so we have our alpha unit binding to our adenylate cyclase, and just like the G protein coupled receptor, we need ATP coming in from inside the cell to go to adenylate cyclase as well. And so what I'm going to do, I'm going to draw this in black just so the arrows don't look confusing. So we have our ATP, or our energy source, going to adenylate cyclase. And so ATP is going to be broken down into two things. And if you remember correctly, it's going to be cyclic AMP and 2-phosphate. So we have our ATP broken down into CAMP, or cyclic AMP, and 2-phosphates. So what's going to happen is cyclic AMP is going to activate protein kinase A. So I'm just going to abbreviate that PKA. So it activates, let me see if I can put this here. Okay, so it activates protein kinase A. And protein kinase A is going to cause a dephosphorylation of proteins. So I'm just going to put dephosphorylation. And I apologize for my handwriting. I'm writing on a screen and it's not very pretty, and I'm sorry if it's a little too messy. but I will again walk you through it if you can't read it. So hopefully just my words will be able to get the picture across. So what we have already happening here, going back to ATP going into adenylate cyclase and being broken down into CAMP or cyclic AMP and 2-phosphates. So cyclic AMP is going to activate protein kinase A. Protein kinase A will then cause a dephosphorylation of proteins. And this, in turn, will close potassium leak channels. And so when potassium leak channels are closed, it goes back to the drawing of depolarization, repolarization, hyperpolarization. So it goes back to this picture here that I'm going to draw. And I'm going to draw it in red so we can kind of tell the difference here. So it goes to this picture, if you will, right? So again, you have to remember what depolarization is, repolarization, and hyperpolarization. So I kind of drew a line down the middle because we know that on one side of it is depolarization and on the other side it's going to be repolarization, correct? So this potassium leak channel closing, it actually causes for depolarization. So it causes for depolarization. So if we remember correctly, depolarization is going to be on this side of the graph. So closing of potassium leak channels in turn causes depolarization, which leads to an EPSP, an excitatory mechanism. So it leads to excitation of that synapse. So what's going to happen is we're going to cause the depolarization because of our closing of potassium leak channels.